have been degreased and we have new stuff here, so today should be a good day. Okay, we're on for lecture number 10. So what I want to do first is go over homework 2, the reliable intuition question. So are there any questions about that? Yes. They're not working? I don't know. Is anybody back there? He was there. Maybe took a bathroom break. Okay. Technical difficulties are being resolved. All right, we're ready to go. So, are there any questions about homework 2? That's what I want to discuss now. All right, so homework 2 was the reliable intuition one, and the interesting part was part B. And it was fairly easy to do, although I asked you to explain it, and everybody gave some kind of explanation, but none of them really made any sense. Some were at least syntactically correct, but didn't make any sense. Some of them didn't make any sense at all, as far as I could tell. But I didn't take off any credit as long as you attempted a discussion. Also, I should say for the future, please write your answers. If you didn't do this, please write your answers in the downloaded cover sheet, and please show all your calculations and use mathematical notation, and follow the directions, whatever they may be. Okay, so the idea is that we have a random variable x, which corresponds to the intervals between arrivals. So this is the first x, and then there's the second x, and so forth. And then there's some point t, and the t cuts one of these intervals in two pieces. So we'll call this value r for remainder of the interval. We'll call this value a for age of the interval, and we'll call the whole interval I. And r, by symmetry, is an expected value is half of I. And we imagine that we generate these x's. So we get the x's by picking from an urn, and we keep on picking them until for the first time the sum of the x's exceeds the point t. Then we look at the particular x that covered the point t. We call that I, and we want to calculate its expected value and its average value from the simulation. And the idea is that x in part B is equal to y plus u, where y is a random variable whose distribution is discrete as follows. The probability that y is equal to 1 is equal to 9/10, and the probability that y is equal to 11 is equal to 1/10. Yeah, this is much better when the markers are new and the board is clean. I think it's clear now. Okay, so what you do is you generate a y according to this distribution, and then you add to it a constant x. And the interesting thing is, a constant u. And the interesting thing is that as u gets larger from 0, at first the graph for the expected value of the remainder goes down instead of up. So if you draw the graph, there's u. There's the expected value of the remainder. In the context of the taxi, if the x's are the times between taxis, then r is the amount of time you wait for the taxi. And if you draw the theoretical graph, you'll see that it starts out here. In fact, the initial value is 2. Is that right? Let me see. I have the answers here. No, actually, the initial value is 3.25. That's when u is equal to 0. And then as u increases, the expected value of the remainder goes down instead of up, reaches a minimum, and then it rises. And it reaches the minimum when u is equal to 1. And that expected value is exactly 3. And then when you run the simulation, you see that, in fact, the simulation points agree with that theory. And so the question is, why is that? That certainly seems to be counterintuitive by most people's intuition. Okay, so the expected value of y from the formula now is equal to the values the random variable takes, which are 1 and 11, times the probability it takes those values, which are 9/10 and 1/10. So simple arithmetic shows you that this value turns out to be 2. Then you want to calculate the variance of y. And the easiest way to do that is to calculate the second moment and then use the formula that relates the variance to the moments. So the second moment would be given by the square of the values the random variable takes times the probability it takes them. And simple arithmetic tells you that that value is equal to 13. Then you want to calculate the variance of y. And the variance of y is the expected value of the square, the second moment, minus the square of the first moment. So that's equal to 13 minus 2 squared, or 9. Now you want to get the expected value of x. And the expected value of x is the expected value of y plus u, because the definition of x is y plus u. The expected value of a sum is the sum of the expected values. But the expected value of u is u because u is a constant. So this becomes the expected value of y plus u, or in other words, 2 plus u. Then you want to calculate the variance of x. The variance of x is equal to the variance of y plus u. Now, the variance of a sum is the sum of the variances if the random variables involved are independent, and they're independent because u, in fact, is a constant. So therefore, this would be equal to the variance of y plus the variance of u. But the variance of u is 0 because u is a constant. So that's the variance of y plus 0, or in other words, it's the variance of y, which is equal to 9. So that means that the expected value of the covering interval, which you're told is given by this formula, although it's not derived, that's equal to the expected value of x plus the ratio of the variance of x to the expected value of x. So what's surprising here is that the expected value of I is not equal to the expected value of x, but in general it's larger than the expected value of x by this ratio. And the only time that this and this are equal is when this term is 0, and that term is 0 only when the variance is 0. In other words, only when x is constant. So in any kind of stochastic process, if these intervals are not constant, if they have some random variation, then the average interrupted interval is going to be larger than the average interval. Now, in the case of the case A, where the x's are exponential, then we argued by the Markov property that this should be exactly equal to twice that. And that occurs from mathematics because for the exponential, the variance is equal to the square of the mean. So that means that that this ratio is the mean squared over the mean, or the mean. So it's e of x plus e of x, which is 2e of x. But that just proves it. That doesn't really explain why it is. Apparently, it has something to do with the fact that the interrupted interval is biased. It's not statistically the same as the x's of which the interrupted interval is one of them. So the assumption that most people make is that since you drew the interrupted interval from the urn with the x's, therefore it must be a typical x. But what I'll show you in a moment, and what maybe you can see from this diagram, you might realize, is that the interrupted interval is going to, on average, be larger than the x, because you're more likely, all other things being equal, to interrupt a big interval than you are to interrupt a small interval. So the size of the interrupted interval depends on two things. It depends on the frequency with which the various lengths occur, and it also depends on how long they are. So this bias of the length, that's the thing that is new and has to be pointed out here. Now, when you plug into this formula, that is, when I plug the values for the expected value and the variance into that formula, it turns out to be equal to 2 plus u plus 9 over 2 plus u. So when you plot that as a function of u, it's easy to see what's going on, because as the u gets bigger, initially, this value gets bigger and this value gets smaller. And initially, this value dominates, and so the sum gets smaller. But then it turns around, and this value dominates, and that value has less and less influence, and then the average length of the interrupted interval becomes linear with u, which is what you would ordinarily expect. So that's mathematically explains it, but that's no explanation. So the question is, why is that? So let me draw a picture here, which I think should convince everybody, give you understanding as to what's going on. So first of all, let's take the case when the u value, the constant that I add on, is equal to 0. So when u is equal to 0, that means that the probability that x equals 1 is equal to 9/10. And the probability that x is equal to 11 is equal to 1/10. Okay, so what happens? That means that when this diagram is generated, you're reaching into this urn and you're pulling out intervals, and 9/10 of them have value 1, and 1 out of every 10 of them has value 11. Now, they don't come out in that particular order, but in the long run, if you were to look at this over zillions of these guys, you would see that roughly for every 10 of them, 9 of them have value 1, and 1 of them has value 11. So what I'm going to do for the purpose of insight here is I'm going to take these intervals, of which 90% are 1s and 10% are 11s, and I'm going to reorder them so that I have 9 1s and 1 11, and then 9 1s and 1 11. So because statistically it's the same thing. So that means that the diagram is now going to look like this. So I'm going to have, let's see, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then here's 20. So here I have 9 1s and 1 11. So this is the frequency with which these x's occur. Now, what's the probability that the interrupted interval I is equal to 1? Because the interrupted interval is one of the x's, so it must either be 1 or 11. What's the probability that it's 1? Well, here's the intervals in the proper frequency. Now all I'm going to do is pick a point at random between 0 and 20 and see what kind of interval I intercept. Well, obviously, the probability that I'm going to intercept one of the 1s is 9/20. So the probability that I equals 1 is equal to 9/20, and the probability that I is equal to 11 is equal to 11/20. Right? Everybody see that? Make sense? Okay, so that means that the expected value of the interrupted interval is equal to the values the random variable takes times the probability it takes those values. And by simple arithmetic, that turns out to be 130 over 20, or in other words, 6.5. So the average interrupted interval is 6.5, even though the average x we decided was what? The average x was 2. Now, the average r is 1/2 of the average I, so that would be 3.25. So the average r the average remainder, the average time you have to wait for the taxi, is 1/2 e of I. That's by symmetry. And so that's going to turn out to be equal to 3.25. And that's the value that I drew on the graph right over here. Okay, now let's take the case where u is equal to 1. Now, if u is equal to 1, then what does the diagram look like? Okay, so here I'm going to draw the same kind of diagram. Now, when u is equal to 1, that means that the x's can be either 2 or 12. The probability that the x is equal to 2 is equal to 9/10, because the x will equal 2 whenever y is equal to 1. So the probability x is equal to 2 is 9/10. And similarly, the probability that x is equal to 12 is equal to 1/10. So now I'm going to draw the same kind of diagram here that I drew here, except that 90% of the intervals are going to be 2, and 10% of the intervals are going to be 12. So now the picture will look like this. Here is 2, 4, 6, 8, 10, 12, 14, 16, 18, and 30. So now I've laid out the intervals so that 90% of them are 2s and 10% of them are 12s. And so I can imagine that I have these repeated cycles of length 30. And then I pick a point out at random. Okay, let's see. Let me go over. Well, let's see where I'll do this. I always run out of space here. Okay, so continuing here, then I could say this. What's the probability that the interval that I pick out at random now is equal to 2? Well, between 0 and 18, the intervals are all 2, and between 18 and 30, the intervals are all 12. So the probability that I'm going to pick out at 2 should be equal to 18 over 30. And the probability that I pick out at 12 should be equal to 12 over 30. So now I do the same thing with this distribution that I did over here. That is, I'll calculate the expected value. So let me erase. Okay, I'll erase this here. So the expected value of the covering interval I is now given by 2. That's the value the random variable takes, times the probability it takes it, which is now 18 over 30. Plus, with probability 12 over 30, it takes the value 12. 12 over 30. And now simple arithmetic shows that that's equal to 180 over 30, or in other words, 6, which means that the expected value of the remainder, which is half of that, is going to be equal to 3. So when the I is equal to, when the U is equal to 1, the average remainder is 3. When the U is equal to 0, the average remainder was 3.25. So in other words, you can see that from the graph that when I increase the U from 0 to 1, that the value of the remainder dropped from 3.25 to 3. And then the similar arithmetic will show you thereafter that the values rise. Okay, so to my mind, that explains it. That shows that the reason that you have this strange effect is that there is a bias introduced in the sense that when I pick the x's out of the urn, they occur with the frequency that's given. But when I lay them out on the in time, and then based on that frequency, I then pick them out at random, that means that I'm biasing to pick out longer intervals, because all things being equal, I'm more likely to land during a long interval than I am during a short interval. And so in this case, this particular example, this bias just happens to work in such a way that from this diagram you can see that the probability that the average interval that's picked out, because of this bias, at first, as the interval lengthens, the average length of the selected interval decreases, completely in contradiction to almost everyone's intuition. Now here, it's sort of easy to see once you draw the diagram what's happening, and at least I can immediately see now exactly what the principle is. It's interesting that this is all encapsulated in this formula. Where did I write it down? I guess I erased it. Or did I write it down? Yeah, it was up here. In any event, it's interesting that it's all encapsulated in that formula. That takes care of every case, and I haven't shown that, although we'll get to that later on in the course. But where this comes into play in queuing theory, for example, I'll give you an example. There's an interesting model, which I hope we'll get to by the end of the course, called the vacation model. With the vacation model, you have something like this. I'll draw a diagram here. Well, first let me say a polling model. These things are related. With a polling model, what happens is this. I imagine that I have a sequence of queues, and I have a device that polls the queues. And when it polls a queue, it asks whether or not there are customers waiting. And if there are, those are the customers, it serves those customers, and when it's done serving them, it moves to the next queue. And in general, there are customers waiting in each of the queues. And so in the polling model, the server moves from queue to queue, and the question is, what are the blocking probabilities? What are the waiting times in the individual queues? This has applications in telecommunications, where, for example, in a local area network, where this may be polling a station, and it serves the messages at that station, and then when it's done, it moves to the next station. That's one application. Another is in manufacturing, where maybe it does some work here, and then when it gets done with that work, then some machine setting is changed, which is the equivalent of saying it switches over to some other kind of work and does that work. And then when that's finished, it switches to the next one and so forth. So you can see lots of potential applications for this. Now, one way that this is analyzed is in terms of what's called the vacation model. In the vacation model, you have a single server, and you have a queue forms. And then when you're finished serving that queue, then you go away for a length of time called the vacation. And at the end of the vacation, you come back. And if there are customers waiting at the end of the vacation, then you serve them and all their descendants until there's no one waiting, and then you take another vacation. And if when you come back to the target queue, there is no one waiting, then you just keep taking vacations until there is. So the vacation then models the length of time that you spend serving the other queues if you're doing polling. Now, if I look at the vacation model, then, or equivalently the polling model, but remember the polling model is much more complicated, because with the vacation model, I simply specify how much time the server spends away from the target queue. With the polling model, it's harder to specify, because the length of time I spend away depends on what happens in the other queues. So there's an interaction there which makes it more complicated. But if we just look at the simple version of it, I serve the queue, and then I go on vacation. Now, the number of customers that are waiting in the queue when I return from vacation depends on how long the vacation was. If I model the vacations in the, for example, the way I've modeled this homework problem, then what happens is that if you make the vacations longer, then the waiting times in the target queue will be shorter, because even though the vacation times will be longer in distribution, they will be shorter in terms of being interrupted by new arrivals. So the end result is that by making the server take a longer vacation, I actually make it more efficient and make it do more work. So you could take the converse of that, and I say we're going to get to this in the course. This is what makes this stuff interesting. Converse is that if I have a particular system that's working here, I can possibly make it work better by forcing the server to remain idle that is, take a longer vacation, because as the mathematics there shows, the end result will be a more efficient operation. In other words, in analogy with this problem here, the remainder, the length of time it takes from when you arrive until the end of the interval is shorter if the interval gets longer. So in the vacation model, the end of the time from an interrupted vacation until the end of the vacation is shorter, even though the vacations are longer. So this is very strange, and in the complicated context of a polling model, you can't see it, because all you can do is observe that when you solve this kind of thing, that's the way the numbers come out, but it's hard to understand why the numbers come out that way. But then you could see that this is actually a manifestation of the same problem, which is that the longer vacations are more likely to be the ones that are interrupted. And, well, I'm not really sure how that explains it. All I know is that when you take the vacation model and you make the vacations have exactly the same description as they were here, that will be one of our homework problems, the end result is that the waiting times for the target queue get smaller. So we'll see that. That'll be a homework problem later on in the course if we get that far. But it's very strange, because people in manufacturing, for example, had the option when they designed these systems. What they tried to do was they tried to minimize the length of time that the server was away from the target queue if they wanted to do the most work possible with the target queue. And then they found that they could actually do more work here if they forced the server to remain idle rather than to have it come around as quickly as it could. In other words, they introduced forced idle time into the system, which seems to be contrary to anybody's intuition, makes things less efficient, but it actually makes things more efficient. Or it could, depending on the particular distributions involved. So we'll see that. Okay, so I think now that this explains it in an intuitive sense. Any questions about that? Do you believe it? Does it all make sense? Okay, so let's get back to the stuff in the book. We were talking about the Erlang loss system. And what we had done last time, Erlang loss system. Let's see, it was section in the book. Okay, section 3.3. The Erlang B system or Erlang loss system. I'll just write Erlang B. Now, before we got to that, we had defined some things. We defined, well, let's see, I think okay, we had defined the carried load. The carried load is the average number of busy servers. So it's the summation of j pj when j is less than s, plus the summation of SPS when j is not less than s. Now, for the Erlang B, there's only one term here, because for the Erlang B, you have the probabilities from 0 to s. So it turns out that for Erlang B, A prime, carried load, calculated by plugging the Erlang B probabilities into this formula and rearranging, simplifying, gives you the following result. A times 1 minus B of S and A. This is called the carried load, and it can be viewed as being the offered load minus the lost load. It says that the carried load, which is the average number of busy servers, is equal to the offered load times the fraction of the load that is lost. Excuse me, the fraction of the load that's carried. And by multiplying this out, that says that the carried load is equal to the offered load minus the lost load. So this is offered, this is lost, and this is carried. When you use those terms, then everything seems to make sense. But remember, this is proved because of the definition of carried load as being the average number of busy servers. Now, this also gives you a better interpretation of what offered load is, because you can see that if I let S be infinity, that means that I would have no losses, because I would have an infinite number of servers, so nobody would ever be dismissed from this system. So in that case, the probability of loss would be 0, and the formula tells you that the carried load is equal to the offered load. So that means that the offered load can be interpreted as the number of Erlangs that the system wants to carry or wants to have carried, and the difference between what it wants done, which is the offered load, and what it actually does, the carried load, that reflects the load that's lost. The units are called Erlangs, and remember that the formula for the offered load was the arrival rate times the average service time. And these units are called Erlangs, E-R-L-A-N-G, Erlangs, after A.K. Erlang. Now, if you look at this formula here, it's not obvious that multiplying the arrival rate times the average service time would give you the average number of busy servers if there were sufficient number of servers so that no customers were ever lost. But this formula says that, and in fact we'll be able to prove this in another way, in a more general way later on in the course, which is called Little's theorem. So I'll write down the name now, but we'll get to it later. Little's theorem. Okay, now, I think that's where I quit last time. I asked you to calculate, well, almost where I quit. This is equation 3.5 in the textbook, right here. Also, by the way, this stuff on Erlang B is given on page 179 of the Bertzekitz and Gallagher book. I'll call it B and G. But it's given in much less detail, and in fact he doesn't even discuss the notion of carried load, which I'll show you is really very important. Okay, now, in the book, starting in the next section, let me look first of all at exercise number 6. I discussed this last time. Exercise number 6 says, I want to calculate this Erlang B formula. Remember that Erlang B is given by this relatively complicated formula. So suppose I had large values of the offered load and the number of servers, for example. This would be a complicated thing, a difficult thing to calculate. For example, I could easily imagine a system with 100 or 1,000 servers, say. How are you going to calculate something like this? And it turns out that there's an easy recursion, and exercise 6 asks you to prove that this is true, but the proof is simple because it's just arithmetic. That is, it's just ordinary algebra. And I'll write it like this. The Erlang B formula for A Erlangs of offered load and N servers is given by A times B of N minus 1A divided by N plus A times B of N minus 1A. And that's valid for N equals 1, 2, and so forth, with the initial condition that the Erlang B for 0 servers and A Erlangs is 1. So this is an important result. And in fact, what I'm going to ask you to do in the future when you calculate the Erlang B is to use this recursion. Now let me give examples, a couple of examples of how this is used. So let me look at exercise number 4 on page 82. Okay, exercise 4 on page 82. It says, let's see. All right, it says, consider an Erlang loss system with 10 servers. Measurements show that about 1% of the arriving customers are lost, denied service. It is estimated that the rate of request for service will double over the next year. How many servers must be added so that the probability, the grade of service will remain the same? Well, let me read this again. How many servers must be added so the system will provide the same grade of service to the customers in the face of the increased demand? Okay, so it's worthwhile to look at this graphically. Here's the Erlang B formula plotted against the offered load. And in fact, these are the graphs on page 316. So to start with, we have, it says there are 10 servers. So here's the graph for 10 servers. So here's S equals 10. And it says that we have observed, we think that the probability of blocking is 1%. I think it was 1%. Yeah. And the load is going to double. How many servers do we have to provide so that we will continue to give the same grade of service? So if the probability of blocking is 10%, then from the graph you could see that the offered load must be approximately 4.5 Erlangs. So if it's doubled, it's going to go to 9 Erlangs. So what I want to do is I want to find the curve that is closest through this point right here. 1% blocking 9 Erlangs, but lies below it, which means that if I have that many servers, then my probability of blocking will be less than 1%, but if I had one less server, it would be more than 1%. So I could see from the graph that there's a curve that goes right by here. The closest one, according to the graph, would be S equals 17. So the answer is, well, if I have 1% blocking now in 10 servers, if I add 7 more servers and the load doubles, I'll still have the same probability of blocking. So that's the way engineers would use this, because what they're trying to do is they're trying to determine how many servers to provide such that the grade of service is whatever the criterion happens to be. Then I think I asked a question like this. Let's see, I had that written down here. What did I just do with that? Okay, how can this stuff vanish when I had it right in front? Ah, here it is. Okay. Okay, so here's the question. Suppose that I say this. Find the minimum value of S such that the Erlang B probability for 100 Erlangs is less than or equal to 1%. In other words, I have a system, I estimate the offered load is 100 Erlangs. What 100 Erlangs means is that if I had an infinite number of servers so that everybody who arrived got served, then the average number of busy servers, average number of customers in service at the same time would be 100. Now, I want to know how many servers I have to have so that if I have that demand, the fraction of calls that are lost will be less than or equal to 1%, carry 99% of the calls. So what I need to do is I need to solve the equation that says that I want to set, for example, the Erlang B of S and A for 100 equal to 0.01, which means I want to solve A to the 100 over 100 factorial divided by a sum of terms like that is equal to 0.01 and find the value of, excuse me, no, I have that wrong. The A is 100. So I have A to the, I have 100, that's the A. 100 to the S over S factorial, and I have to find the value of S that satisfies that. So the way I'm going to do it is I'm going to use the formula that I wrote right here and write a little program for it. And then you can, I'll write it in BASIC. And in fact, I have it written on a little calculator. I've got a calculator that I bought. This is a Radio Shack, I think it's called a PC 8 or something like that. Yeah, no, PC 6. Anyhow, I bought this around 20 years ago when PCs were just coming out, shouldn't say just coming out, but PCs were just becoming widely available. And I bought it because it takes BASIC. And at the time, I was teaching a course at George Washington University called Telecommunications Traffic Engineering. It was a course that was taught by the Department of Continuing Education. And the people who took the course, it was a 3-day course, and the people who took the course were all working engineers. Their tuition was paid for by their company, and they were trying to learn how this stuff applied to telecommunications. And in those days, these calculations were relatively sophisticated. Now anybody can do it, but for most of the people who took the course, I always said that just learning how to make this calculation that itself, if you didn't already know it, was already worth the tuition. Okay, so I'm going to write in a program which is actually going to calculate this simply by iterating on it. So statement number 10 is an input statement, and it asks you to input the offered load and C, which stands for criterion. And then it's going to iterate. So statement number 20 starts out and takes the initial condition, B is equal to 1. And statement number 30 increments the number of servers by 1. And then statement number 40 is the essential statement. It says that the Erlang B is equal to A times the previous Erlang B value divided by N plus A times B. In other words, statement number 40 is the basic representation of this recursion. And then statement number 50, having calculated the Erlang B, I compare it with the criterion. If the Erlang B is less than the criterion, then I want to increment the number of servers by 1 and do it again. So I'll go back up to 30. And I keep on doing that until for the first time the Erlang B, I should have said greater than the criterion. So if the Erlang B value is greater than the criterion, that means I have to add servers. So I keep on looping through this until for the first time I drop through statement number 50, and then I print my answer, 60. Print N, which is the number of trunks or servers you have to provide, and B is a check, which tells you what the probability of blocking will be for that value. Okay, so then when I run this thing, I simply put in a numerical value of A, which in this case I want to be 100, and a numerical value of C to be the 0.01. That's the criterion. So I'm going to put in A equals 100 Erlangs, and I'm going to put in C equals 0.01. And the question is, what am I going to get out? Anybody have a guess? How many servers do I have to put in order to handle 100 Erlangs with a probability of blocking of no more than 1%? Well, if you run it, the answer will turn out to be 117. So I need 117 servers. And the probability of blocking at that time would be 9.79007113 times 10 to the minus 3. In other words, just slightly below 1%. I can do that on this calculator. It takes about 15 seconds. Of course, on a computer, it takes about an instant. When I'm doing that, I've run through this loop Well, in this case, I will have run through that loop 117 times. So in fact, in the process, I'm calculating the Erlang B for an offered load of 100 Erlangs for every number of servers between 1 and 117. So if I put in a print statement, I could print out all those values, and I would have a table of the Erlang B for 100 Erlangs. Of course, I could run it for any number of Erlangs, so this turns out to be very useful. Okay, any questions about that? Okay, so here's an interesting, I think, observation. Suppose that I took my 117 servers. So if I have 117 servers and I offer to it 100 Erlangs, we know that the probability of blocking would be 1%. But suppose that for some reason I wanted to divide up my traffic so that I had 50 Erlangs offered here and 50 Erlangs offered here. And I want to have the same grade of service. So that means that I have to have a certain number of servers here, a certain number of servers here. Of course, they're going to be the same. What I want to have was 1% traffic. Well, it turns out that if I ran the same program and I said I have 50 Erlangs of traffic and I want the probability of blocking to be no more than 1%, how many servers do I have to have? The answer would be 64. So the same thing would be true here. So in other words, if I took my traffic and I divided it in half and offered half of it to one group of servers and half of it to another group of servers, the total number of servers necessary to carry the load with the same probability of blocking would be 128, which is 11 more than 117. So those extra servers, that represents lost efficiency, because when I split my traffic up and offer it to two groups, there's a certain probability that that all of these servers will be busy, but not here. So that means that I'm going to be less efficient. In other words, the bottom line here is that if you can, it's always better to aggregate your servers and to have as large a server group as possible. So all of the things being equal, large server groups are more efficient than small server groups. Okay, so you can get lots of information out of here. Let's see, I did mention the formula for carried load. And now I'd like you to think about something with respect to homework number 1. In homework number 1, I didn't ask you to calculate the carried load, but I could have. And so what I want to do is I want to introduce a new statement. So go back to homework number 1, and I want to introduce statement number 205, which is this. The sum of the service times is equal to the sum of the service time plus the present service time. In other words, what I'm going to do in homework 1, just to make it more complete, instead of just calculating the probability of loss, I want to calculate the carried load. And I claim that the way that I can calculate the carried load in the simulation is to simply sum up the service times of all of the customers that are carried, and then at the end, statement number 285, I'm going to print. And what I'm going to print is the total work done divided by A. A, remember, in that simulation is the total time simulated. And that should equal a carried load. And I'm going to explain later why that should be true. But I want you to think about it, and I'd like you to run this thing and convince yourself that when you add these two instructions to your simulation, that in fact the value that will come out here will be the same that will agree with this formula right here, right? In our particular case, for that problem, the A was 9.6 Erlangs, and the number of servers was 10. So you calculate this, you run the simulation, you print out the total amount of work done divided by the total time over which you did it, and that should be the same as the carried load. You might say, yeah, of course, because obviously the total amount of work done is in some sense the total load, and A is the total time, but remember the carried load is defined as the average number of busy servers, and so it's not clear immediately why the two things are the same. But if you run the simulation, you'll see that they are. In fact, remember now, this is for Erlang B, which presumes that you have Poisson input. But in fact, if you calculate this expression right here, 9.6, that's the offered load, times 1 minus k over nc, you will get the probability of loss in every single case. K, remember, was the number of customers that overflow. NC was the number that arrive. So this was actually the actual fraction of customers that are lost. So if I take the offered load and multiply it by 1 minus the fraction that is lost, I will get the load that's carried. However, it won't be given by this formula unless you have Poisson input. But whether or not you have Poisson input, it'll still be given by this. So if you go back to homework 1 and you run the simulation and make these checks, everything should work out. Now, I'm not going to ask you to hand this in because it's too simple-minded, but I'd like you to do it because later on in the course when we look at homework number 3, these concepts are going to become, it's going to be helpful. Okay, let's take a look at the next homework problem, which is exercise number 10 on page 85. Okay, so I'm going to get back and I'm going to prove this thing right here later. Exercise number 10, page 85. It says we have two independent Poisson streams of traffic called low priority and high priority traffic, and they're handled by a primary group of 10 servers. Low priority customers who are blocked on or overflow from the primary group are cleared from the system, whereas high priority customers who overflow the primary group are routed to a backup of overflow servers. So we have a diagram that looks like this. Here's my group of servers, and I've got high priority traffic. I'll call that AH. So that's going to be the number of Erlangs of high priority traffic. And I've got low priority traffic, AL. And they both share the same group of servers. But the way I differentiate between high priority and low priority is that high priority have another shot. So there's maybe S servers here and C servers here. Whereas the low priority, if they don't get carried by the original S servers, they're lost. So it's sort of obvious that the high priority customers are going to get better service because they have another auxiliary group of servers to go to. Now, according to the statement of the problem, it says that according to measurements, the high priority customers require an average of 12 minutes for service and arrive at a rate 20 per hour, of which 2 per hour overflow. Okay, so they arrive at the rate of 20 per hour. So for AH, the lambda is equal to 20, and it says that they require an average of 12 minutes. So the average service time is 12 minutes, but if lambda is in arrivals per hour, then tau must be also measured in hours. So therefore, 12 minutes is 1/5 of an hour. So I'm not sure why I put this in here, in part because, well, it's important to recognize that we have to have everything in the same units. But actually, I think it's some kind of reflection of a psychological scar. because I remember that when I was in grade school that we would learn something like, for example, how you calculate the area of a square. And the answer would be, well, you would multiply the length times the width. And then they would give you a test. But in a test, they would make the length in yards and the width in feet. And, of course, since I was really concentrating on the essence of the thing, I would forget to change from feet to yards or yards to feet, and I would always get the problem wrong. And it really drove me crazy because it seemed like everybody was emphasizing trivia. So I have this scar on my soul, and so what can I do? So I'm carrying it along, and you're suffering for it. Okay, so what this means is that the offered load for the high priority customers is lambda h, so that would be 20 times 1/5, or 4 Erlangs. So AH is 4 Erlangs of traffic. Okay, so you're told that you have 4 Erlangs of traffic, and you're also told this. You're told that the measurements show that the probability of loss is equal to 2, it doesn't say the probability. What it says is the measurements show that they overflow at the rate of 2 per hour. So if they overflow at the rate of 2 per hour and they arrive at 20 per hour, then the probability of loss must be 2/20ths, or 1/10, 10%. So we have a probability of loss of 10%. Now how does that relate to the Erlang B? And the answer is, well, let's see. I know that I have 10 servers. So here's my Erlang B. What's the offered load? Okay, now I'm going to tell you, but I haven't proved, but we'll worry about this later in the course. But this turns out to be an important fact, and it's not at all intuitive, is that if I have 2 Poisson streams offered to a group of servers on an Erlang B basis, that is, this is a Poisson stream, that's a Poisson stream, they're independent, and the blocked calls are cleared, then the probability of loss given on that group of servers is obtained by simply adding the number of Erlangs. So the number of Erlangs here would be equal to 4, that's the high priority traffic, plus A sub L, the low priority traffic. So that's a fact. Yeah, question?
I'm wondering, for that, what you just said, that would intuitively that would make sense if there wasn't the extra server C, because there's a lower chance that a high priority message gets lost than a low priority.
Okay, wait. Okay, you're saying that somehow or other this has to do with this C, but I'm saying no, let's forget that this C exists.
So that's what I'm saying. Is that
Okay, so the C is out of there, but I'm going to argue that it doesn't really make sense because it's not necessarily true that the service times here are the same as the service times here. So I'm just saying that I have Poisson streams because they occur at random, but I'm not going to require that whatever population this is and whatever population this is have the same service time distribution functions. They could be completely different. So what turns out to be true is that the effect of adding 2 independent streams, if they're Poisson streams, even though they're made up of different distributions of service times, has the effect of simply adding the number of Erlangs. So there's 2 important points here. One is that these, for example, could be exponential service times. These could be constant service times. These could have one rate. These could have another rate. Whatever it is, there's a certain number of Erlangs here. There's a certain number of Erlangs here. The effect of those 2 streams on this group of servers is just as if those 2 streams were combined together. And so in this case, I would have a number of Erlangs equal to 4 plus whatever AL is, which I don't know at the moment. That's the first thing. The second thing is that because of pasta, whatever the probability of loss is for these guys, it's the same for these guys. Because whatever probabilities result on these servers, since this is a Poisson stream and this is a Poisson stream, they both see the same thing. They both see whatever states there are. So if this is busy 15% of the time, then this stream will arrive, will see all servers busy 15% of the time. And this stream will see all servers busy 15% of the time, even though these could have wildly different numbers and different distributions. Okay, so there's two factors here. One is that both streams see the same thing if they're Poisson streams. The second is that if this system has block customers cleared, then the effect is just as if I combined those two streams and added the number of Erlangs. Now, if you think this is obvious, then let me tell you that when we get to the case where there's queuing, in other words, the block customers don't wait on a queue, then it's not true that if I have two streams, that the effect of the two streams is the same as if I combine them and added the Erlangs together. So it works only because the block customers are cleared. If the block customers waited in a queue, it would not be true. Yes?
Didn't we prove that earlier in the course by saying that if we have block customers cleared, then the Erlang B formula works regardless of service time as long as the input service not processes?
We did say that, but and in fact, you could make the argument that the proof is embedded in that. But so maybe I should say yes, because if we have queuing, then it's not true that we have insensitivity to service times. So the insensitivity to service times is the thing that makes this work. Okay. But still, the nonlinearity of the formula, to me, always makes it surprising that if I just take the two loads and add them, even though they're comprised of different service times, different averages, nevertheless, the effect is exactly the same. The only thing that counts is the product of the arrival rate and the service time and the fact that they are Poisson and independent. And otherwise, it doesn't matter. Okay, so that's sort of surprising and at least worth pointing out. Okay, so it says in this case that we have a certain probability of blocking. We know the number of servers. We know the offered load for this stream, but we don't know the offered load for this stream. So from this, we can figure out what the offered load from this stream must be because we know what the probability of blocking is. So in other words, this means, this statement here implies that 4 plus the number of Erlangs in the low priority traffic must equal 7.5 Erlangs. Because just as before, we could figure out that if the probability of blocking is 10% and we have 10 Erlangs, 10 servers, then the total offered load must be 7.5 Erlangs. So knowing that, we can get this from the diagram or from solving the equations mathematically with the formula for the Erlang B. So that means that I know what the offered load must be for the low priority traffic. It must be 3.5 Erlangs. So therefore, if the offered load here is going to double, then the probability of blocking for the high priority traffic, which will also be the probability of blocking for the low priority traffic, will be what I would get if to 10 servers I offered 4 plus 2 times 3.5, or in other words, 11 Erlangs. And now if you just calculate the Erlang B for 11 Erlangs offered to 10 servers, it turns out to be 0.26. So that means that the question says, if the overflow rate of the low priority customers doubles, by what factor will the overflow rate of the high priority customers increase? And so the answer is 0.26, 0.10, or 2.6. So in other words, it seems as if there's not enough information here, but there actually is. What it says is, I have a high priority stream, I know the number of Erlangs, I know the number of servers, and I know the overflow rate. I don't know what's here, but I'm going to tell you that this is going to double, and I want to know what the effect is going to be over here. And the answer is the overflow rate is going to go from 10% to 26%, or in other words, it's going to be 2.6 times larger than it was before. So this works for Erlang B, but it doesn't work in general for other kinds of queuing systems. So Erlang B has nice robustness properties. Okay, any question about that? That was part A of the problem. Okay, now part B asks this. it says, if the overflow group handles the overflow traffic on a BCC, blocked calls cleared basis, is it legitimate to use the Erlang loss formula to decide how many servers to provide in the overflow group? In other words, what I'd like to say here is something like this. I'd like to say, well, let's see. When this guy doubles, that means that this guy's overflow rate is going to increase by a factor of 2.6. So that means that the overflow rate now, here it was 4. So if I multiply by 4 by 0.26, that means that the number of Erlangs, or the overflow rate here, is going to be equal to 1.04 Erlangs. So it was 4 Erlangs. Now, with the increase, it's 1.04 Erlangs here. Okay, so the question is, let's look at this guy right here and say, now what I'm going to do is I'm going to calculate the probability of blocking here by saying that I have an offered load of 1.4 Erlangs, and then figure out from that the number of Erlangs that I have over here, and then take the ratio of that to that in Erlangs, 4 Erlangs, and the result will be the probability of blocking overall for the high priority traffic. So the question is it legitimate for me to look at the overflow traffic and assume that I can use the Erlang B formula again to decide what's happening in the overflow group? Okay, that's the question. Maybe I could ask it another way. Here let me look at another system, because there's sort of a distraction here in that the essence of the question is what's going on here. It really has nothing to do with this. But I can't calculate what's going on here because this is a complicated system. I can't calculate it directly. So what I'm going to do is I'm going to look at something that's simpler but has the same principle, for which I can actually make some calculations. So here's the example I want to use, because we've already looked at part of this. Let's start off and say we have a group of servers, and there are S equals 10 servers, and we have an offered load of 9.6 Erlangs. The reason I'm using 9.6 Erlangs and 10 servers, a simple system like that, is because that's what we did in the previous homework problem. Okay, so for this, we have some answers. We already know. So we have some overflow traffic. For one thing, we know what the carried load is. The carried load is equal to the offered load times 1 minus the probability of blocking, B of 10A. And in our case, A is 9.6, and that means that we have 7.7180 Erlangs of carried traffic. So when you go back to your homework 1 and you run the simulation with the instruction that I gave you, the carried load should turn out to be approximately 7.7 Erlangs. Now, we have an overflow load here, which I'm going to call alpha 1. And the overflow load, that's the lost load, is equal to the original offered load times the fraction of the original overflow load that overflows, the fraction of the original load that overflows the primary group of servers. So that's A times B of 10A. A, of course, is 9.6. So this is going to turn out to be 9.6 times the Erlang B for 9.6 Erlangs offered to 10 servers. We already know what that is. That Erlang B is 0.1960. You had to calculate that in homework 1. And that turns out to be equal to 1.8816. Yes? Yes, I could. There are different ways I could do it, and because loads work like average values, because they are average values, you could think of them in terms of water flowing. So what this says is that I'm going to offer 9.6 Erlangs. I'm going to carry 7.7 Erlangs. So therefore, the difference is going to be about that number of Erlangs. It should be exactly, except for rounding. But that's the same thing as saying that the amount that overflows is what's offered times the fraction that that is lost here, and so that gives me the overflow. Okay, so 9.6 Erlangs are offered here, 1.8816 Erlangs overflow. Now what I'm going to do is I'm going to offer that to another server. And I want to see what the effect of that one more server is going to be. Okay, so there's going to be an overflow there, which I'm going to call alpha 2. Okay, now what's that overflow? Well, now I have 11 servers altogether. So therefore, alpha 2 is equal to the original offered load A times the Erlang B with 11 servers, which is equal to 9.6 times, now I have to calculate the Erlang B of 9.6 Erlangs offered to 11 servers. And that turns out to be 0.1461. When you multiply that out, that turns out to be 1.4026. Okay, so where we are now is that the overflow from the primary group is 1.88 Erlangs, and the overflow from the whole system is 1.40 Erlangs. Okay, so what I would like to do is say, well, or this is what I'm going to do. I'm going to say, well, obviously, what happens here is that the probability of blocking for on this group of one server, the probability of blocking in that one server is alpha 2 over alpha 1. Alpha 2 is the number of Erlangs that overflow this server. Alpha 1 is the number of Erlangs that are offered to that server. And in fact, that's equal to A, B of 11A divided by A, B of 10A. Of course, the A's cancel out. So it's the ratio of those Erlang B's. In any event, it's this ratio. It's 1.4026 divided by 1.8816, which by arithmetic turns out to be 0.7454. So that's the actual probability of loss, because it's the ratio of the overflow load to the offered loads. That's the probability of loss on that server. Okay, now the question was, because I'm asking it over here in a more complicated situation, can I use the Erlang B formula to figure out what's going on here? In other words, can I use the Erlang B formula right here? Because here I have one server. I know what the offered load is. So what will the probability of blocking be? Okay, so suppose I wanted to calculate the Erlang B with one server and an offered load of 1.8816 Erlangs. So I make that calculation, and it turns out to be 0.6230. Okay, so the answer, calculated by calculating the ratio of the overflows, is that the probability of loss is about 75%. But from the Erlang B formula, the probability of loss is only about 62%. So the answer is, over here, that apparently it's not legitimate to use the Erlang B. Okay, so the question is, why is this? This one apparently is true. If I use the Erlang B, I get a value that's too low. What's wrong? Why can't I use the Erlang B to describe my overflow traffic?
Because the overflow is a soft process.
Right. How do you know that?
I'm just guessing because of the length bias we saw earlier, that a longer, or I'm not sure if it's a longer or a shorter process has a greater probability of being worked on at one time, thereby biasing.
Okay. Okay, the question is, what was the question? The question is, why doesn't the Erlang B apply? And your answer is half correct. Okay, it's because it's not Poisson. That must be because the requirement for the Erlang B is that I have Poisson arrivals, and it doesn't matter what the service time distribution is, and the block customers are cleared. Well, in this case here, or similarly in this case here, I have block customers cleared. Doesn't matter what the service time process is. It doesn't work, so therefore the problem must be with the Poisson process. But the reason that you gave, which has something to do with that bias, I'm not sure if that's right. Of course, you can always argue that since you're describing things intuitively, maybe that's, who knows. Okay, let me give what I think is a more convincing argument as to why overflow traffic is not Poisson. And first, let me say why this is important. Because in telecommunications networks, overflow typically, well, maybe looks like this. Here's an example of a simple network. I have a group of servers that connects city A or node A to node B. And then I have node C, and I have servers that connect them and servers that connect them. And so typically, the way I might design such a system is I might say, all right, I'll offer my traffic between A and B, but if all the servers are busy, rather than simply increasing the number of servers between A and B, I'll alternate route. Of course, there's a complication because now a call wants to go between A and B, needs two trunks simultaneously, one in each link instead of one. But forgetting that difficulty, I would like to be able to say that the load offered to this group right here is the sum of the direct load plus the overflow load. But I can't say that and be accurate because, as we've just seen, the overflow load is not Poisson, and so the Erlang B formula does not fit. So that leaves two questions. One is, why is the overflow load not Poisson? And then the second is, what do we do about it? And so let me answer the first one. The what do we do about it, that's more complicated. Okay, so are there any questions about what the question is? So what I'm trying to show, because I've already illustrated it here, is that overflow traffic is not Poisson. And here I show it exactly because I can make the exact calculation. Okay, now let's look at overflow traffic. Suppose that I had a system, and let's say I've got, that's the total number of servers I have. Maybe that's 3, let's say. So what's going to happen is an arrival will occur, I go to state 1, and then state 2, and so forth. Anyhow, eventually, I get over here to where I go to the blocking state, and I stay there a while, and then I go down. And then I bop around a bit, and then I get back up to the blocking state, I stay there a while, and then I go down, and so forth. Now, when I'm in the blocking state, in general, customers are arriving, and those customers are going to be lost because they're going to arrive when all servers are busy. So basically what I see here, if I look at a group that receives this overflow traffic, is I see sort of a switch here which goes on and off. When all servers are busy, the switch is on, and when all servers are not busy, the switch is off. Now, for a given measured overflow rate, I'm going to argue that this traffic is more variable than Poisson traffic. And if it's more variable, that is, there's more bunching and spacing, and therefore it's harder to handle, and therefore you need more servers to handle it. Okay, now, one argument goes, if I had Poisson traffic, that means that the times between these overflows are going to be exponentially distributed. If the times between overflows are exponential, that means that there's no memory. So therefore, knowing how much time has elapsed since the last overflow tells you nothing about how much time is going to elapse until the next overflow. But now, if you look at this, I could see that if an overflow has just occurred, then, like here for example, it's reasonably likely that another overflow will occur soon because I know that all of the trunks below must be busy. On the other hand, if a long time has elapsed between overflows, then it's likely that the reason that that has happened is because the trunks below are not all busy, and therefore you would have to have more arrivals in order to make them all busy. So therefore, having a short time since the last overflow predicts a short time to the next, and having a long time from the last overflow predicts a long time to the next, which means that the past influences the future, and therefore you could not have exponentially distributed inter-overflow times, and therefore the overflow process cannot be a Poisson process. And in fact, it's worse than a Poisson process, because what happens is, for the same arrival rate, the arrivals, or the overflows, tend to occur in bunches, with bunching and spacing and bunching and spacing as the switch goes on, off, on, off. So if you have more bunching and spacing for the same number of arrivals overall, that means that the thing that causes the congestion is when the customers tend to arrive simultaneously and ask for the service at the same time. The most efficient system, the best system, is when the customers spread out as evenly as possible, and that spreading out evenness is less likely when I have the on-off switch than if the switch is always on. Okay, so the bottom line is that this exercise shows some interesting things. It shows that for an ordinary Erlang B system, offered loads add regardless of their size. It shows that each stream sees exactly the same probability of blocking, and it shows that the overflow traffic is not Poisson, and therefore, once you overflow the first group of servers, you cannot treat that traffic, you cannot calculate what that traffic is going to do by applying the Erlang B formula, because the Erlang B formula assumes that the traffic is Poisson, and once it's overflow traffic, it's more bunched and spaced than Poisson traffic. And so if you assume it's Poisson, you will underestimate the actual probability of blocking. Okay, so that kind of kills this, I think. And next time I'm going to start talking about the ordered search, in which we have servers, and we assume that the customers arrive according to a Poisson process, and it goes server to server, and then eventually leaves if you have a finite number of servers. And the question we want to ask is, what's happening on an individual server? I want to calculate the probability, which I'll call P sub j hat, which is the probability that a specific server is busy. And the probability it's busy is the same thing as its utilization. It's the same thing as the load carried by that server, as we'll see. And but the load that is offered to that server is not Poisson because it receives overflow from the preceding server. Okay, so if this were a probability problem and you knew no queuing theory, and someone said, I have arrivals occurring according to a Poisson process, and I have an arbitrary service time distribution, tell me the probability that server number J is occupied, that would be a very difficult problem. But using the notion of carried loads and a little bit of queuing theory, what we've learned so far, we can get a formula for this, which will give us the load carried on each server in the case in which the servers are selected in ordered hunt. Okay, so we'll start there next time.